Good evening, all of you.
Yes, sir.
Good evening.
Yeah. So this will be the last topic, probably. So angular impulse and conservation of angular momentum. Now this is exactly similar to what we have dealt with the impulse of a force in the translatory motion and also conservation of linear momentum. So here we have to deal with the angular momentum, right? So all of you should have this clarity here. Just don't treat this as a mathematical expression or something like that. Okay? Now try and understand. This is a particle of mass m. Okay, and if you give it a velocity v bar, right? Then you get a vector. What is this vector? You will get a vector p bar. Okay, p bar is what? P bar is m v bar. So my dear friends, let's look at it like this. Okay, what is this? This is a vector that you have created. This is a vector you have created. There is a particle, mass m. You are given some push and it's having velocity v bar and it has got momentum p bar. Clear?
Yes, sir.
Hello?
Yes, sir. Yes.
Now, if at all, so it's a vector, means it has got magnitude and direction. If at all you want to change this vector, what I say? Change this vector. Change this vector. Cause a change of this vector. Okay? Cause a change of this vector means you should change it by say delta p bar. Then what you have to do?
Apply some impulse or
Why impulse?
like force.
ಬಾಯಿಗೆ ಬಂದಿದ್ದು ಹೇಳಿದ್ರೆ ಬಯಸ್ಕೋತಿ
Answer.
ಅಲ್ಲ ಅದೇ ಹೇಳ್ತೀರಿ ಐದು ಅಂತ ಹೇಳಿ ಏನು ಬೇಕಾದ್ರೆ ಹೇಳೋದಿಲ್ಲ ಕರೆಕ್ಟಾಗಿ ಹೇಳ್ಬೇಕು ವಾಟ್ ವಿಲ್ ಯು ಹೌ ವಿಲ್ ಯು ಚೇಂಜ್ ದಿಸ್ ವೆಕ್ಟರ್ ಓನ್ಲಿ ಬೈ ಅಪ್ಲೈಯಿಂಗ್ ಎಕ್ಸ್ಟರ್ನಲ್ ಫೋರ್ಸ್ ಓನ್ಲಿ ಎಕ್ಸ್ಟರ್ನಲ್ ಫೋರ್ಸ್ ಕ್ಯಾನ್ ಚೇಂಜ್ ದಿಸ್ ವೆಕ್ಟರ್ ಐದರ್ ಇಟ್ಸ್ ಡೈರೆಕ್ಷನ್ ಆರ್ ಮ್ಯಾಗ್ನಿಟ್ಯೂಡ್ ಆರ್ ಬೋತ್ ಇಸ್ ಅ ಕ್ಲಿಯರ್
Yes, yes, sir.
Yes. Yes, sir.
that means if this vector has undergone a change it is only because of the external force. Got it?
Yes,
Yes,
sir.
sir.
Yes, sir.
Now, similarly, so this one is what? What is this? This is linear momentum. Okay? Now, we create one more concept. What is that concept? Supposing there is a wheel, okay? There is a wheel, and if you rotate this wheel, so this wheel is having moment of inertia I about this axis, and if you give it a spin, omega, right? Then
Yes.
what are you going to create? Are you creating some vector?
Angular momentum.
You are creating just like how you created this vector by giving
Velocity.
velocity to that. Here you are going to do the same thing,
Yes, sir.
Yes.
right? And here you will create this vector. What is this vector? This vector is angular momentum. Angular momentum.
Yes, sir.
Okay, denoted by L. Exactly same like this. Now, this angular momentum vector is a vector. It has got both magnitude and direction.
Direction. Yes, sir.
If you want to change this angular momentum vector, what have you got to do?
Provide additional torque.
Provide
External torque.
external torque. Isn't it? See, for this to change, you will provide external force. For this to change, you will provide external torque. Then only this vector can be changed. Otherwise, you cannot change. Okay? Otherwise, you cannot change. Is it clear?
Yes, sir.
Yes, sir. Yes, sir.
Now, if you give force to this body, can this vector change?
So it depends on where you are applying.
See, if you can better coin your answer. If I apply force,
Yes, sir.
can this angular momentum vector change.
Sir, if it's along the line of action, sir, then it will not change, sir. But if it's perpendicular or some other
Line of action of what?
Sir, line of action, sir, like in which like angular momentum, sir, such that if angular momentum is not changing, sir, by applying force, sir, then sir,
If angular momentum is not changing by applying force,
yes,
okay,
then the this it will not change. Like angular velocity.
angular momentum will not change.
sir. But if we like with some angle or we are
Yeah, good. So can you coin it with some better words? If the external force results in a torque on this body,
yes,
see,
Yes, sir.
if the external force creates a torque on this body,
yes, sir.
then this angular momentum will change.
Sir.
That will be better. It will not give rise to any confusion.
Yes.
So that is very clear. See, all the forces that apply on this, okay, may not get converted to angular momentum.
Angular momentum.
One of the illustrations is that if the line of action of the force is passing through the center of mass of a free body,
Yes, sir. Yes, sir.
center of mass of a free body,
Yes, sir.
okay, then it will not cause
Change.
This is one of the illustrations.
Yes, sir.
This is not the only illustration,
Sir.
right? If the body is pivoted and it is rotating,
Yes, sir.
then if the force is passing, if a body is pivoted at some point other than center of mass and rotating about that pivot,
Yes, sir.
then if you give external force to this body, will the angular momentum change?
The same explanation.
Provided here in this case it should not pass through the pivot point.
Pivoted. Yes, sir. Yes.
Got it now? Because you are considering the momentum about the pivot point.
Pivoted.
So have this common sense and put it. I suppose it is clear.
Yes, sir.
Right.
Yes,
Good. Good. Fine. So you must have this idea, angular momentum. Of course, I am showing you a wheel.
Yes, sir.
So I am just showing you a wheel. Okay. Otherwise, you see, now supposing I have y-axis and x-axis, and this is my reference point, and I have a particle here, which is having velocity, okay, v j cap, whose velocity is v j cap, and this is the point of reference. Okay. Now, does this, and of course there is mass for this, does this particle have angular momentum with respect to O?
Yes, sir. Yes, sir, it has.
It will have. And what is the angular momentum?
Yes, sir.
Hello, everybody try to answer.
Yes, sir.
Sir, please give us coordinates.
Yes, sir.
Assume.
It's called.
Assume. See, if nothing is given, then it coordinates the action. Nothing is given, you can always generalize it.
Yes.
But the better way to say is that, sir, you draw the position vector from O to M, draw the position vector, and then the angular momentum of this particle, L bar will be equal to R bar cross
P bar.
M
P
V.
bar.
NDX data. Yes.
Yes, sir.
Yes, sir.
Isn't it? R bar cross M V. I wrote M V bar
Yes,
V
sir.
bar. It is the angular. Okay. Now, so you can see that this particle keeps on moving, okay, and this angle goes on changing. So the angular momentum of this particle will change with the time, right or wrong?
No, sir.
And
What about others?
Sir, no, sir.
Why?
No, sir.
Sir, it is-
Yes. This gives you what? The perpendicular distance. This gives you what? If you open this, you will get M R M means sin theta.
Yes.
So this r sin theta is the perpendicular distance. That will not change, and therefore the angular momentum will not change.
Yes, sir.
Clear?
Yes, sir. Yes, sir.
Now, if a force acts on this body,
Yes, sir.
if force acts on this, will the angular momentum change?
If it acts perpendicular, sir, then it will change, sir. If it lacked along.
ಸಮಾಧಾನವಾಗಿ ವಿಚಾರ ಮಾಡ್ತಾರೆ.
Ah, sir.
Will the angular momentum change if force acts on this particle?
Sir, if the force acts along
Yes,
the direction of
yes, sir, it will always.
It will always change. See here, one brilliant point word. So it will always change. If force acts on this, it will always change. Yes or no?
Yes. Yes.
Agreed?
Yes, sir.
Dhiman, do you agree? If you don't agree, say don't agree. Why are you hesitating? If you don't agree, you say don't agree. See, nobody is great here. Okay, everybody are learners here, including me. If you disagree, say I disagree, sir.
I disagree.
I disagree. Hemant is disagreeing. Come on, Hemant, why do you disagree?
Sir, I think, sir, like that particle length, sir, that point mass in, sir, like unless if the force acts in the same direction in its velocity, sir, it will not create any change in angular momentum.
If the force acts along the velocity vector, it will not change. Yeah? Come on, friends, what's wrong with all of you? Just now, 2 minutes ago, all of you said that force must cause torque.
Yes.
The force must cause torque. What is torque? Torque is R bar cross F. Correct?
Yes.
Supposing I apply force in this direction. So R cross F bar will be 0. Hello?
Yes, sir.
Hello?
Yes, sir.
Yes. Yes. Yes, sir.
Then why did you all give wrong answers? If the force acts along the position vector, always. What did I say? Always. That means whether the body is here or here. So when the body is here, the force must be in this direction, along this line. If the force is always along the radial vector or radius vector, either in this direction or in ulta direction, then R cross F is 0.
Central force.
Then such a force is called central force.
Yes, sir.
When I taught you gravitation, I told you.
Yes, sir.
Yes.
See, Earth is moving around Sun, right? There is gravitational force acting on the body.
Yes, sir.
The velocity of the Earth is changing. You know, when it comes closer to the Sun, its speed increases. When it goes away, its speed decreases. And all the time, the velocity of Earth is changing along its orbit,
Yes, sir. Yes, sir.
right?
Yes, sir.
Its momentum is changing.
Momentum. Yes, sir.
Its linear momentum is changing.
Yes, sir.
So that means force is acting on the body. What force is acting? Gravitational force.
Yes, sir. Sir,
What force is acting? Gravitational force is acting. So gravitational force is changing the linear momentum of Earth.
Yes, sir.
But the gravitational force is not changing the angular momentum of Earth.
Yes.
Why? The gravitational force is always radial.
Radial. Yes, sir.
Yes.
Gravitational force is always radial. See, this is the orbit of Earth. This is SUN Sun. And when the Earth is here or here or here, the direction of force is always towards Sun.
Towards him, yes, sir.
Okay, it's always towards Sun. Okay, and you see the force is, and what is this? This is the radius vector, and the force is always along the radius vector. So therefore, this force, gravitational force here is central force,
Yes, sir.
and therefore the angular momentum of Earth is conserved.
Yes, sir.
Yes. Yes, sir.
Understood? And that is why Mr. Earth is always in the orbit. Okay, but the linear momentum of the Earth keeps on changing
Yes, sir.
because of external force. Correct?
Yes, sir.
Good. So based on that only you have the second law.
Yes, sir.
Kepler's second law is based on this aspect only.
Yes.
We did the derivation based on this only.
Ah, sir.
Done. So,
That previous example,
what previous example?
in quantum times, the previous.
ಅರುಣ್ ಮುಂದೆ ಹೋದ್ರೆ ಹಿಂದೆ ಹೋಗ್ತಾನೆ ಏನು ಮಾಡೋದು ಗೊತ್ತಾಗಲ್ಲ.
Say that force if it acts radially, the tangential component of that, like f cos theta part, sir, it is increasing that distance r, sir, like r sin theta, sir. So angular momentum changes.
Why do you want to unnecessarily confuse yourself? See, torque is r bar cross f bar, no?
Sir, even if sir, even if the radial component is increasing, the other component of force will increase the velocity. It increases the linear
So
momentum.
it should increase the
Totally
That's what I'm telling. If one is decreasing, other is increasing. But the total change is 0.
Sir, but
See,
then both are
Yes,
increasing.
Pardon, both will not increase. See, it is very simple, man. Torque is R bar cross F bar.
Theta will
Okay, see what is happening here? You can see here, no, the theta is increasing, no.
Yes.
Theta is increasing, no. R, the magnitude of R is increasing, but theta is also increasing.
Yes, sir.
So we are measuring, if you measure this theta, R sin theta is this theta we should take. So R sin theta will be constant. Okay, that is the reason why the angular momentum will not change if the force is radial. This is basics. Clear?
Yes, sir.
Ah,
Yes, sir.
we have already discussed this earlier. Okay.
Yes.
Now one more illustration. Say now one car is moving in this direction. Okay. Another car is moving in this direction. Right? So if I take this as a reference, this point as the reference point. Okay. Then this is moving with velocity u1 bar constant, and this is moving with velocity u2 bar constant. Now the angular momentum of car 2 with respect to 1. Is it changing or is it constant?
Constant.
Why?
Relative velocity.
Relative velocity. Again, okay, why?
Perpendicular distance between them is also.
See, the perpendicular distance will not change.
Yes, sir. Yes, sir.
Okay,
Yes, sir.
and no external force is acting.
Yes, sir.
Here in this case, you see no external force is acting.
Yes, sir.
So torque is 0. See, look at it like this. Torque on this system is 0. So therefore angular momentum is conserved. As simple as that.
Yes.
What about linear momentum? It is also conserved because no external force is acting. See, if external force is acting on a system, then linear momentum has to change. But if this force results in torque, then angular momentum will change. Otherwise, it will not change. As simple and as sweet as possible. Okay? Right.
Yes, sir.
Okay, fine. Now, conservation of angular momentum of system of particles. I will explain to you. The meaning is tau bar is equal to dLO bar by dt. That is, you are taking the angular momentum about some reference point O. The reference point can be anything. And dLO bar by dt is what? Tau external 0.
Yes, sir.
Okay. Since the torque of all internal forces nullify each other, so it's only due to external force. Okay. So L initial is equal to L final. That means delta L bar is equal to 0. This is the principle of conservation of angular momentum. Same like the principle of conservation of linear momentum. Can anybody state the principle of conservation of linear momentum? Faster.
If the net external force acting on a system of particles is 0, its linear momentum remains conserved.
Excellent. So, if the net external force on a system of particles is 0, then the linear momentum of the system is conserved. Very good. Well said.
Yes, sir.
Well said. Okay. So, same thing here. If the net external torque acting on a system is 0, okay, then the angular momentum is conserved. See, on a system, I am telling you, system of particles, same thing here, system of particles. So, the individual particles' angular momentum can change. But the sum total of the angular momentums will remain same because the net torque is 0. Net external torque is 0.
Yes, sir.
Now, again, I think all of you are familiar with this term, F bar dt. So, F bar dt is what? Impulse of a force. You remember long ago?
Yes,
Huh?
yes, sir.
So, simple. So, tau bar is equal to R bar cross F bar dLO bar by dt. So, now we will now just create a vector here, R bar cross F dt bar. This becomes dLO bar. Then we used to write integration F bar dt is equal to delta PL. Delta P bar. Remember?
Yes, sir.
You are friends here, yes or no?
Yes, sir. Yes, sir.
So this is it. So R bar cross F bar dt will be equal to delta LO bar. Integration F bar dt is equal to J bar is equal to impulse of a force.
Yes, yes.
Clear? Simple. So we knew this, same thing is going to be applied here. So R bar cross J bar is equal to delta L over angular impulse. And this is called angular impulse. Okay, so there simply integration F dt. Sorry, F bar dot dt we call it as linear impulse. So this is angular impulse. So just multiplied by R cross. R cross F bar torque.
R bar plus P bar and angular.
Angular moment. R bar plus P bar angular moment. R bar plus J bar angular impulse. Got it now? So this term should be simple. So torque of an impulse about a point equals the change in the angular momentum of system about that point. Now again you see, now don't have any misconception about the impulse. Of course, by definition, what is an impulse? Large force acting for a short duration of time. So when you say large force, that means now other forces can become insignificant. Do you remember one numerical that we had worked out? Right? It becomes insignificant. For example, a ball is coming and you hit with a bat. Okay, so there you see, we consider the impulse. Okay, there the gravitational force acting on the ball becomes insignificant if the time of contact with the bat is very, very less. If the time of contact with the bat and ball is more, then the gravitational force will not become insignificant.
Yes.
So usually you see, but so for a very short duration, when the force interacts, then we use the word impulse. But frankly speaking, see Newton's second law. Okay, what happens at the instant the force is acting on a body? What will happen? So you get F is equal to m into A. Right? Then what happens during the interval of time when the force acts? Then you used to use the impulse function. Integration F bar dt. What happens during the interval of space? F bar dot dx bar. We use the concept of work.
Okay.
Right? Basically that's it. So we are integrating with respect to time. We use impulse functions, and we are integrating with respect to space. Then we use work functions. Right? And if we directly write F bar is equal to m into A, so F is equal to m into dv by dt, then it is instantaneous.
Yes.
That's all. Okay. Now, conservation of angular momentum. So summation tau O bar. That is, you are taking all the torques with respect about point O in the time interval t1 to t2, and if this is equal to 0, then initial torque is equal to final. See, initial angular momentum is equal to final. The condition for zero net angular impulse required for conservation of angular momentum is fulfilled in the following cases. Now everybody aram se learn. I am making all these videos and I will give it to you. There are some 60 videos. I am making it, all this RBD, I'll give you all of them. I'll make it public and give it to all of you. Put the right thumbnail and all. You can aram se learn. Don't worry. Yeah, because now time is short. You just contemplate on understanding.
Yes, sir.
The condition of zero net angular impulse required for conservation of angular momentum can be fulfilled in following cases. If no external force acts, the angular impulse of all the axes about all the axes will be 0, and hence angular momentum is 0. So naturally, if external force is 0, no question of angular momentum. If net torque of all the external forces or torque of each about the axis vanishes, angular momentum will be conserved. So net torque is 0. Then also if all external forces are finite in magnitude and concerned time interval is infinitely small, the angular momentum remains conserved. This point is extremely important.
Yes,
if all the external forces are finite in magnitude and concerned time interval is infinitesimally small, that means this force is acting for a very, very short duration of time. Concerned time interval is very small, then the angular momentum remains conserved. Now, who can explain this? Come on, apply Newton's laws and everything that we have studied about motion. What is the basic thing? Well, are you thinking, in what direction are you thinking?
Inertia.
Yes, excellent, inertia.
Yes, sir.
So you see, these bodies have inertia, and therefore angular momentum, if it has to change, then there is something which opposes the change in angular momentum.
Yes.
What opposes?
Moment of inertia.
Moment of inertia.
Yes.
Yes, sir. Moment of inertia.
So, however small the moment of inertia is, moment of inertia is moment of inertia.
Yes.
So, changes cannot take place instantaneously.
Yes.
Just like
Yes,
how
sir.
in linear cases, dv by dt cannot change in 0th time.
Okay. Yes.
So, dp by dt cannot change in 0th time.
Zero. Yes.
Yes, sir.
Okay, dLO by dt cannot change in 0th time. So, if the time interval is extremely small, okay, then that means now, see, the force is applied or to a system or the torque is applied to a system, but you have to give finite, it is small time interval for action to take place. It cannot happen instantaneously because inertia will come into picture.
Sir, this infinite like timetable, like what range?
No, don't ask me that way. Inert means very, very small.
Very, very small.
Very small.
Sir, this is only true for angular momentum, sir. Like
For linear also it is
Sir,
true.
linear momentum, like force it provides some like,
No, that's what I'm telling. That's what I'm telling. See, even if you say F is equal to M into A, what is F is equal to M into A? F is equal to M into dV by dt.
Yes, sir. Yes,
Even there you see, you have to allow certain
time.
time interval.
Yes.
Don't ask me how much you should be the time. Very small. See, it all says that, if the inertia is large,
Yes, sir.
if the inertia is very large, then you need to give a larger time interval for the force to cause any significant change in its momentum.
Yes.
That's what is to be understood. Okay? Finite in magnitude. See, finite in magnitude, that's important. And the concerned time interval is infinitely small, then the angular momentum is conserved.
Yes,
If a
sir.
system of rigid body changes its moment of inertia by changing its configuration due to internal forces only, then its angular momentum over any axis remains conserved. Can anybody explain this? You say it is completed in your college, this chapter.
Yes, sir.
Then you should tell this. You should explain this. Everybody has an opportunity to explain. Please explain. See, you are all getting trained for world-class examination.
Sir. Sir, if you consider a system of rigid bodies, the internal forces exerted by one rigid body and another, there will always be mutual impact.
No, that's not exact. That's not a thing. That doesn't bring out the thing here. See, you should bring out by changing its configuration due to internal forces. Okay, I will tell you. Now, if you go to a nice park, okay, children park. So you should not bring up adult. So you can see that there is something like this with a handle. Have you seen something like this?
Yes, sir.
It has got handle at the end, and there is one more handle at the center.
Yes, it will rotate.
And this can rotate. Do you know this?
Yes, sir. You will do it.
And Ruptungbatta it is there. In fact, Sharan's batch. Neela, are you there?
Yes, sir.
So to your brother, when he was in 8th standard, I took him to Ruptungbatta. Sharan's batch or his senior's batch? Sharat was not his batch. Sharat was his classmate? I don't remember. Anyway.
Yes,
Same batch, right. So I had taken all the students to Ruptungbatta. They were in 8th standard. And there, this toy is there. Okay. So I made all these children to stand here. 1, 2, 3, 4. Okay. Then I rotated this with omega. They were all standing and I rotated it. Okay. So it started rotating. So all of them were standing. Okay. So here one boy was standing, here another boy, here another boy. Okay, here another boy was standing. So it was rotating. Then I asked all of them to slowly move to the center. I ask all of them to slowly move to the center. Hello, are you with me?
Yes, sir.
Yes, sir. Yes, sir.
Then as they move to the center, the speed increased
Yes.
by itself. By itself, it was rotating. As soon as they started moving to the center, its speed increased.
Yes, sir.
And when I asked them to move back to their original position, the speed of rotation automatically decreased.
Yes, sir.
And I told everybody, see, there is
Even we do this, no sir. Like if we are sitting and rotating, sir, we tend to move our bodies inwards to make it fast. Like if we are only two people or one person.
correct. So let's concentrate on this. See, don't distract me, Abhi. Now, see, I was trying to explain this, and everybody are focusing what is happening. Okay, so here you see the speed automatically changed. So I told, oh, see, automatic. We did magic now. Its speed is changing. And there are other onlookers also in Murthy, but they also say, hey, they were looking at it. So what is the magic here? The magic here is that, you see, with respect to this axis. So this person M1, M2, okay, M3, M4. So if the radius is R, so what is the moment of inertia of the system about this point? So it will be summation Mi Ri. This is the moment of inertia.
Yes, sir.
Okay. And I pushed it. When I was pushing it, what I was doing? I was applying force here. Okay. So F into the distance. What was I doing? I applied torque.
Yes, sir.
And therefore, its speed increased from 0 to omega.
Yes.
And then I stopped applying force. So no external torque is applied.
Yes, sir.
At that moment, the moment of inertia of this was Mi Ri 1 squared.
Yes.
Okay, because all of them were there. So omega. So the angular momentum was I1 omega 1. Okay. Now what happened? All of them moved to the center. So as they moved to the center, this R reduced. It did not become 0. So therefore, the angular momentum now becomes I2.
Yes.
No external force is acting. So therefore, the torque, the angular momentum must remain same. So this angular momentum decreased, and therefore this has to increase.
Yes.
Yes, sir.
Got it, all of you?
Yes, sir.
Okay. So you'll find wonderful things. And as your friend Abhinav was pointing out, see, if you go to the gym, so there will be some circular disc. So usually we stand on the circular disc and we do this so that your trunk becomes small. Okay, the shape. Okay. So there you can do an experiment. You can stand on that disc, and it is rotating disc. You hold 2 dumbbells in your hand. Dumbbells in your hand. Not very heavy. Okay, it's moderate. And then ask somebody to rotate you. So with the dumbbells you start rotating like this. Okay, you are rotating. And then what you do, you take the dumbbells inside. Understood?
Yes.
Then you will start spinning fast. And then you put it away. Then your speed will automatically decrease. Rotation will automatically decrease. What happened here? Change in the configuration.
Yes.
Change in the moment of inertia.
Yes.
So here also what did you do? You change the configuration. By what? By internal forces. See, these people have to apply force to move from here to here.
Yes.
Yes.
So internal forces were used to change the configuration, not external forces. And therefore, the angular momentum of the system remains constant. Is that clear, friends?
Yes.
And then the popular dance, ballet dance. Okay, so you can see, a wonderful lady, she will be with ice skating usually. Okay, so one feet will be like this. You can't see my feet. So with only 1 feet, she starts rotating with only 1 feet like this. And then what she does, she brings her feet close and does like this. Then she will be spinning very fast.
Yes.
And then again she releases, she will slow down. What is that? Angular momentum is concerned. Using her internal forces, she changed her configuration. So the moment of inertia changed. Right? And therefore, the spinning action will increase.
Yes.
That is it. See, I think all this should have been discussed in your college. Then what else is there in this? If all the external forces are, if a system of rigid bodies changes its moment of inertia by changing its configuration due to internal forces, only its angular momentum about the axis remains conserved. If we denote the moment by this, I1 omega 1 is equal to I2 omega 2.
Yes.
The principle of conservation angular governs a wide range of physical processes from subatomic to celestial world. See, even the basic thing, see, atomic radius. So you said the MVR, the angular momentum of the electron is conserved, is equal to NH by 2 pi. We started with this. So you see, the electron is not moving in any circular orbit. The electron can move anywhere around the nucleus. It has no fixed path. But wherever it is moving, its angular momentum will not change. By itself. By itself will not change. If you excite it, okay, that means by giving external energy, okay, then yes, you cause it to go to the next orbit, its angular momentum will be different in different orbits. But you have to cause the change.
Yes, sir. Sir, when we consider rigid bodies, sir, and we say that they have angular momentum, means that they are rotating about a certain axis, sir. And sir, now if we take an electron, sir, it is we can consider it for all practical purposes as a point mass, sir. So then how can we define angular momentum for that when it is
MVR.
what? Fixed orbit?
Just now I told what MVR. M is what? Mass of the electron. V is what? Speed of the electron. R is what? The Bohr radius.
Sir, but it is actually not moving in that fixed orbit, no, sir.
Hello. Now don't drag me into atomic structure. You have studied. Now when we are deriving the Bohr radius, we have to consider the electron is moving in a circular orbit. Okay. And then we define what is orbit. Orbit is a region where the probability of finding the electron is the maximum.
Yes, sir.
90% maximum. Okay, and that's how we define the concept of orbit. Right? Orbital and all. Anyway, next chapter I will be dealing with that. We will discuss these things in detail. I will do the derivation using all the concepts of wave and all this we have studied. Angular momentum and all. We will do it. Spinning of a skater. Just now I explained to you. A student on a rotating table. Correct? You can see here the dumbbells are out and he brings the dumbbells close. Then spinning will increase.
Yes. Yes.
Great. Angular momentum of body is combined translational and rotational motion. So angular momentum in this one, LP is equal to LCM plus R bar cross PCM. Common example, this one. I hope all of you know this.
Yes, sir.
Okay. All of us know this. Okay. Right?
Yes, sir.
Some of you are ominously quiet here. You don't know what to do with you.
Yes, sir.
See now I was just going through the video and I was remembering Arun's face like this and all the other day when we solved this problem. Okay, that is pivot problem. A rod is pivoted here, the rod is pivoted here, and its center of mass is here. The center of mass of the rod is here, and when you release the rod, this rod will be released and it will come to the vertical position.
Yes.
So the center of mass will come here. Okay. Now, if you consider this point O, okay. So if you consider this point O, the moment of inertia about this point of the rod will be ml square by p.
Right. Yes.
And then when you are considering here, okay, you will only consider that the rod has rotated, and you will calculate the kinetic energy of rotation. Okay, R I naught omega. At some point it's this is omega, you do it. Now the same expression you can do it by splitting this into, that is the total kinetic energy. Total kinetic energy is this. It's simply rotation. Or the total kinetic energy can be written as translated kinetic energy plus rotational kinetic. Now rotational kinetic energy here is about O. Here the rotational kinetic energy I will take it about C.
Center of mass.
So what do I do here? I will now first consider this rod is rotating about its center of mass.
Yes, sir.
So that means this rod will rotate and come, assume it will come like, it will become like this. Then you translate it.
Yes, sir.
So that is how you will separate it.
Okay.
Yes.
So you, for this, assume that it is rotated about the center of mass here only. I am not drawing it properly, about this point only.
Yes, sir.
Okay. So then you will say, what is the rotational kinetic energy? IC omega. Omega will not change. Okay. Then you consider its translatory motion. So at some point its velocity is v. Then it becomes half m vc square. Half m vc square. What is vc square? The velocity of the center of mass. Got it? So that is how we separate it out.
Yes, sir.
Center of mass. Or, and we proved that this is equal to IO omega square. Half IO omega square. We proved this in the last exam.
Yes.
I hope now it's clear.
Yes.
Now Arun is happy. See, that's the advantage. You know, I was watching the video and I could hear Arun asking questions, and then I answered him, but then I felt, oh, no, I should have taken an example like this and answered. It will be better. Anyway, it's helping me also, the technology, to understand my class better. Because when I hear my own voice, okay, and my own lecture, you know, I'm feeling so excited because it's very strange feeling. Sometimes I am learning from my own lectures. Okay, that is the beauty of technology these days. Where R is a position vector and so it's. I hope you understood this.
Yes, sir.
Right. So for a change, let's quickly solve this problem.